Welcome to lab report number 2 of Introductory Physics with Labs. In this lab we're going to investigate the motion of a falling object, both with and without drag. According to the objectives of the lab, we captured video to analyze in Tracker, and then we built computational models of an object that originally fell from rest with gravity only, then with air resistance added, and then additionally in the what if segment we're going to talk about what might happen if it had an original downward velocity. Let's look at the mathematics involved. The weight force is simply the mass times acceleration due to gravity in the negative j hat direction. For the drag force, we look at both magnitude and direction, and we used a parameter b as was suggested, and I think that's considered to be essentially our coefficient of friction. It might be. We were asked to consider the square of the velocity in our model, and it's negative because our drag force is always going to oppose the motion of our object. All right. When we look at our tracker data, I decided to drop a coffee filter. So we went and found some space in a hallway and dropped the coffee filter using the base plate of the door as the scale to set the scale for it, setting the origin in the middle of the filter as we dropped it. So that's sort of the experimental setup. You can look at the graph and see that we reached a constant slope or terminal velocity fairly quickly. I took the time and the Y position data from Tracker and inserted that into a Google document, as you can see here. The first graph I did, I wanted to just take a look at the position of the coffee filter itself, and then from there we'll proceed into the code. We wrote code starting with the Lab 2 starter program, and in the interest of time, I'm going to stick to just the calculation loop. I did measure the mass of the coffee filter. It was about 27 grams, which made it 0.0027 kilograms. This is where I inserted the code for the weight force and for the drag force. And then for the net force, we just simply added the weight force plus the drag force. In the code, we have the constant of proportionality here, and we'll talk about that in a second. In the first run through, we set b equal to 0, and so without a drag force, running the model and then inserting the data into Google, we can see here that what the model predicts and the actual filter position is very different. There was a significant change due to the action of air resistance. So when I went back and added drag force in there, which I did by just playing with this number. I played with the proportionality constant until we reached a point where it matched the data. Putting that into the Google document and graphing again, we can see then that when I added the drag into here, the actual model, the model prediction, and the actual collected data from Tracker agree very closely. There's some discrepancy in the middle that I was frankly unable to explain in the different things that I did with this, but be that as it may, I think the model and the actual data agree fairly readily. Now moving into the what if portion, what if we had an original downward velocity? So I took the program that I had and I set the negative 5 meters per second as a downward velocity. And if we run the program, we can see we still reach terminal velocity, actually extremely quickly. And you can tell by the curve on the graph that we actually decelerate into a constant velocity. So in my conclusion, and what does it mean? It tells me then that given enough time that an object can free fall, if it's falling with a drag force, will eventually reach a constant velocity. It'll reach a terminal velocity if it has enough time. And that concludes my lab report.